Problem 5.54 or 6.48 from the given textbooks. For details, please see the description below. An adiabatic gas turbine expands air at 1300 kilopascals and 500 Celsius to 100 kilopascals and 127 Celsius. Air enters the turbine through a 0.2 meter square opening with an average velocity of 40 meters per second and exhausts through a 1 meter square opening. We need to determine the mass flow rate of air through the turbine and the power produced by the turbine. The next step is to write a balance of energy. We're going to write it in terms of rate of energy at different positions in the system. Therefore, we have E dot in minus E dot out is equal to the change of the rate of energy in the system. Since the turbine is steady, this quantity is equal to 0, and it reduces to the E dot in is equal to E dot out. Please note that we're going to use 1 for the inlet and 2 for the outlet. In this case, we have a turbine. So notice that we're going to have an inlet, position 1, and we have an exit or an outlet, position 2, and this turbine is going to create power W dot. Therefore, the amount of the rate of energy going in is going to be simply the mass flow rate times the enthalpy at the entrance, the kinetic energy at the entrance, and we're going to neglect the amount of potential energy since there is not much high distance between the entrance and the exit. This is equal to the mass flow rate, enthalpy at the exit, kinetic energy at the exit, plus the amount of power produced by the turbine. In order to solve this equation for the power produced by the turbine, we need first to calculate the mass flow rate, and we also need to calculate the velocity leaving the turbine. In order to do that, we're going to do mass flow rate is equal to density, velocity, and cross-sectional area. This could also be rewritten in terms of a specific volume, velocity, area, divided by specific volume. We're going to use the quantities at the entrance since we know the velocity at point 1. So this is going to be velocity 1, cross-sectional area 1, specific volume at point 1. Then what we're going to do is first calculate the specific volume for the inlet condition. Specific volume, we're going to use it, we're going to calculate it using ideal gas law, and we have that P V is equal to RT. Therefore, specific volume at the inlet is equal to RT1 divided by pressure 1. And for air, we're going to use a constant of 0.287 kilopascals meter cubed kilogram Kelvin. And if we substitute the value, this is what we get, 0.287 kilopascals meter cubed kilogram Kelvin. The value of the temperature at the entrance is 500 Celsius, so we convert it into Kelvin plus adding 273. This is Kelvin, and we divide it by the value of the pressure, which is equal to 1300 kilopascals, and then this is going to give us 0.1707, and the units are going to be meter cubed per kilogram. If we substitute the value of the specific volume at the inlet, the velocity of the inlet to be 40 meters per second, and the cross-sectional area at the inlet to be 0.2 meters per second, we find that the mass flow rate is equal to 46.88 kilograms per second. The next step is to find the velocity at the exit. For that, we need the specific volume at the exit. We're going to do the same process with the previously. Specific volume at the exit is going to be RT2 divided by P2. If we do the same substitution, we find that the specific volume at the exit is equal to 1.148 meter cubed per kilogram. and then we're going to use the relationship that the velocity at point 2 is equal to the mass flow rate, the specific volume at the exit, divided by the cross-sectional area at the exit. This is derived from this equation. Therefore, we find that the velocity at the exit is equal to 53.82 meters per second. The final step is to find the power created by the turbine, and then we're gonna solve for that value from this equation. The power is going to be equal to the mass flow rate, H1 minus H2, plus mass flow rate divided by 2, V1 square minus V2 square. Notice that we already have the value of the mass flow rates and the velocities. Now we need to find out the value of the enthalpies. Since we have air as an ideal gas, we could do the approximation that the change of enthalpy is simply the value of Cp multiplied by the change in temperature. Therefore, the power created by the turbine is simply going to be mCp delta T plus m dot divided by 2 V1 square minus V2 square. The value for Cp is calculated by using the average value of the temperatures. Notice that we have 500 Celsius and 127 Celsius. Therefore, the average value of the temperature is going to be equal to 314 Celsius or 587 Kelvin. This provides us a value of Cp equal to 1.048 kilojoules kilograms Kelvin. Now that we have the values, let's substitute into the equation. The power produced by the turbine is equal to the mass flow rate, 46.88 kilograms per second. The value for Cp is 1.048 kilojoules kilograms Kelvin, and the change of the temperature is going to be 500 minus 127, and we could write this in either in Celsius or in Kelvin, since the change in temperature for Kelvin and Celsius is exactly the same. Plus, we have mass flow rate, 46.88 kilograms per second, and then we multiplied by the change in the velocities. That is going to be equal to 40 meters per second square minus 53.82 meters per second square, and then this is divided by 2. Over here you have to be very careful in terms of the unit. If you notice, the units in the top part of the equation, kilograms and kilograms cancels, Kelvin and Kelvin cancels, and the unit is kilojoules per second. However, in the second part of the equation we have kilograms meters square per second, and if we transfer these units, notice that it becomes kilograms per second, and this is meters square per second square. For this to be able to transfer into kilojoules per second, you need a conversion that it goes like this: 1 kilojoule per kilogram is equal to 1000 meters square per second square. Therefore, we need this conversion in the second part of the equation in order to have the units matched. Therefore, we simply multiplied up here 1 kilojoule per kilogram, and this is equal to 1000 meters square per second square. You always need to have this conversion when you are going to add the values of enthalpy in terms of kilojoules per second plus kinetic energy. If you do the conversion properly, the value of the power produced by the turbine is equal to 18,300 kilowatts. Please note that for this power to be produced by the turbine, it is required for the velocity to increase, as well as the value of the specific volume in the system.